basic trig, and we start with a favourite, SOHCAHTOA. Now hopefully you remember SOHCAHTOA from school days. The word doesn't exist as such, but we've made it up because it's a memory aid or mnemonic, and it refers to the sine, cosine and tangent of an angle. These are ratios that describe an angle, and each of these ratios is described in two sides. Okay, so there we see sine, as you see, is the opposite side of the hypotenuse. Cosine is adjacent over hypotenuse, and the tangent is the opposite of the adjacent. Now what they mean will be revealed in a few minutes if you're not too sure. First thing you need to do is to remember that these apply equally well to triangles, and especially in a right angled triangle where we've got ABC, and the capital letters are the angles and the small letters refer to sides. Even in textbooks they still use that same pattern. Alright, so all capital letters refer to angles and small letters refer to sides. Now Pythagoras theorem, most people remember this, and in this particular triangle we can say that adding the two sides, that are the smaller sides, squared together will equal the long side. So in other words, if there's an angle of 90 degrees at C, then A squared plus B squared will equal C squared. And here's a typical example, very straightforward, and it won't tax your abilities too much. We've been given a triangle here. This is 6, this is 17. X is the hypotenuse. The longest side is always the hypotenuse. We've got to solve for theta, and we have to solve for x. Okay, now when you look at theta, you've got to decide what ratio can I use, sine, cos or tan. Well, look at the sides that are given. So you've given 6 and 17. 6 is opposite to theta, 17 touches theta, it's adjacent. Now some people say, but hang on Mike, because x also touches theta, isn't that adjacent as well? Well, it is, but the point is that x is the longest side, and by definition that's the unique side, which is always the hypotenuse. So in this case I've got opposite, adjacent, so I choose the tan formula. Here we go. I'll just go through that. We've got the triangle. I'll just bring this down for you a little bit. There we go. There's theta, 6, 17, and here's our right angle. So I look at that, and I look at the two sides that I'm going to use. I define the two sides saying this is opposite theta, which it clearly is. This touches theta, so this is adjacent. Okay, so SOHCAHTOA, T-O-A, OA is there, O and A, so I want the tangent. So now from that I write down this. Tan theta equals opposite over adjacent, and that will fit with the data. Now the question now is, how do I write this out to convince the examiner that I know what I'm talking about? Watch this, the next line is particularly important. I now write down theta, or so therefore theta equals, and this is what we do. We write down tan to the negative 1, and we put in brackets 6 over 17. Now you read this as shift tan. In other words, we've got a ratio, we want to get back to degrees. So showing you on the computer, or rather on the calculator here, I turn it on. Okay, now shift, the little mark comes up, tan, watch what happens. See, tan negative 1. So tan negative 1 means shift tan. Now I put the ratio in, 6 divided by 17, close brackets for good practice, equals. Okay, bingo. In other words, what it's done is it's actually converted this ratio into an angle. 19.44003483. Most of this is meaningless, but I'll show you how to make meaning of it in a minute. Now this is a decimal and this will be degrees. Okay, so let's just revise that again. Shift tan up she comes, and of course Casio prompts with a bracket, which is always a nice feature. 6 divided by 17, close bracket for good practice, and equals. And there we are. Now, you've got this number. You've got this whole string of numbers. Does it mean anything? Well, in most cases, most of these numbers are irrelevant. It's only the first 2 or 3 that you want. You know for a fact that it's 19 degrees and there's a bit left over. Now, the easy way to convert this is as follows. What we now do is use, I'll just write this out, the DMS button. Now, in the older calculator style, it used to be called DMS, which stands for degrees, minutes, and seconds. In the modern one here, you will notice it's got a nice little symbol, an open circle, closed circle with a tail, and then 2 closed circles with 2 tails. That's the degrees, that's the minutes, that's the seconds. So it replaces this older version. And on here, it's just above the button ENG. It's this one. So if I hit that, look what happens. It does it for you. Okay? It actually changes this horrible number 19.44003483, which doesn't really mean very much, to something that is a lot more meaningful, especially to mariners. Okay, so we can now say theta equals 19 degrees, yeah, 26 minutes, yes, 24.13 seconds. So super accurate. Most lecturers and examiners are quite happy if you take it to the nearest degree or to the nearest minute. So we would be quite happy with something like 19 degrees 26 minutes, because the 24 seconds is relevant. Or you can say it's approximately equal to 19 degrees, because this is less than 30. Okay, so that would be quite helpful. Now, it does have that written out in the book. Let's just check this. Note, to do this you need to use Shift-Tan on your calculator. Okay, and we've got 19 degrees 26. Right, the next little bit that we require is to find x. Remember, we had to do 2 things here. We had 6, the right angle, 17. We know this angle now, we've got x. Well, this is pretty easy. The simplest way to do this, there are a number of ways, but the simplest way is to use Pythagoras. So we can say, oh, that's right, Pythagoras. 6 squared plus 17 squared must equal x squared. Therefore, x will equal the square root of 6 squared plus 17 squared. And again, on the calculator, you should be able to do this in one hit. Let's have a look. Okay, the square root. And again, notice Casio prompts with the bracket. Now let's see if we can do this in one hit. 6 squared, yep, plus 17 squared. Now, you've got to be careful here. For good practice, and you'll notice I've said this through a lot of these video constructs here, for good practice, close that off with a bracket. The reason is, if you don't, and you have to add this to something else, plus whatever it is, okay, divided by that, okay, then the calculator thinks it's all in the square root, all right, and you've given it false information. So we'll delete all this rubbish here. That's the point at which I want to stop the calculation. That's the point at which I do the answer, and that will in fact give you the correct answer, which is in your book. And we've brought it back to, in fact, 2 decimal places. There you go, 3, which is more than sufficient to give you the full marks. Okay, so remember, your Casio does that, you must do that. If you don't, whatever else follows will be incorporated in the square root sign. Of course, if you forget this and nothing else follows, there'll be no problem. Let's just show you that again. Okay, it's only important if something else follows. So watch, square root 6 squared, okay, plus 17 squared. Now if I don't put the brackets in, will it do it? Yes. Okay, but I like to put the brackets in because I'm teaching you the right way, okay, and that's important. Now at the bottom of the page, here we are. We're happy with those. We can do those all day long. All right, they're not difficult, and you get into a pattern of familiarity. The bottom line there throws up a little question. Now, what do you do if the triangle is not a right-angled one? Okay, and there are lots of these in the world. In fact, probably most of the triangles you will meet from now on may not be right-angled triangles at all. So then we have to invoke another set of rules. So we can use either the sine rule or the cosine rule, whichever is appropriate. Now, the sine rule, people take to that very quickly. The reason why is not hard to see. The sine rule says this. In a particular triangle, okay, so if I draw one that clearly isn't a right-angled triangle, that's clearly not a right-angled triangle. A, B, C, this then becomes little a, this becomes little b, this is little c. What I can say now is this. A over sine A equals B over sine B equals C over sine C. And that's the same formula as you have in your book at the top of the next page there. Now you only need any two of these, so I can use these two, or I can use those two, or I can use those two. Any two, providing I know 3 out of the 4 terms, I can use them. Okay, if we have a look at that problem in the book there, we've got some values. Consider the triangle below. So let me work through that and we'll see how straightforward this is. It's just really the sine rule is actually a proportion rule. It's a very simple proportion rule. So let's have a look. Okay, so in this particular triangle, if I just redraw it for you, we've got this one where this is A, this is B, and this is C. Okay, so this now is little b, this is little a, this is little c, and we know this is 5. This one happens to be 16, and the angle here happens to be 30 degrees. Okay, so we're up and running. Now, using the sine rule, if we want to find this angle here, we can do it. We say, okay, 5 over sine C equals, now we have a pair because I know this angle and I know its partner, so this is 16 over sine 30. Okay, if you want to check that in your book, you'll find it's completely correct. Now from here, again, mentally I know that I can use the cross multiplication rule. I'll just do it out for you. This is nice and simple, so this can be rewritten as 5 times sine 30 must equal 16 times sine C. I want sine C, so finally if I bring the 16 across, remember to do the opposite procedure. It multiplies there, it must divide there, and wow, look at this. I've got the term for sine C. If I want to impress the examiner, okay, I would say this. Shift sign of 5 sine 30 over 16 equals angle C. I can put this into the calculator, which I've done down at the bottom, okay, and C actually equals, as you see in your book, 9 degrees. Now, if that's 9 degrees, you don't have to work out what B is in the same way. You've been given A, which is 30. You've now found that C is 9. So therefore, using the fact that there's 180 degrees in the triangle, if I now take these two away, I find that this angle B is going to be 141 degrees. Okay, that's a simple way. Always try to find the simple way to work these out. So you've calculated the 9 correctly, you've been given that one, add them together, take them from 180, and finally you get this one. Okay. Now, for side B, if we go back to this problem here, we need to find side B. So you can either use the sine rule, you can do that because B is opposite this angle, we know this one now, or you can use the cosine rule. At the bottom of the page, just to remind you, very quickly I've used the sine rule, 16 over sine 30 equals B over sine 41, and we find that B equals 20.1. One of the problems there is that I've had to use something that I've previously calculated. So can you see that if I've made a problem here, if I've got a bit of a problem with this one, if this is 9, and if it's not 9 in real life, then this is going to be wrong. Okay, so that's the difficulty. Notice the 16 and the 30 were given to me by the examiner. So the basic rule here is use what you are given rather than what you've calculated, unless you can avoid it. Always a good practice that, to remember that one. Okay, now I've just turned the page and I want to show you something that's extremely important here. Now, if you get your calculator for a minute, let's have a look at the calculator again. Turn it on. Now, type in sine 30, close brackets, good practice, equals 0.5. Okay, so sine 30 equals 0.5. We'll cancel that out. Now, sine 150, close brackets, also equals 0.5. Okay, and if you think about it, there's an infinite number of values that you can keep going round in a circle, adding on so many degrees, and it'll still give you 0.5. The question now is this: if I have a problem and I say, right, sine theta equals 0.5, what does theta equal? You will then go and say, oh, I know how to do this. Theta equals shift sine of 0.5, and you would be correct. You would then go to your calculator, you would say shift sine 0.5, close brackets, equals, and you'd say, the answer is 30 degrees. And then the examiner says, yes, you want to get half marks for that. Now, why? The big problem here is that in a real situation, you may have an angle which is less than 90, and we call that acute, or it could be greater than 90, and we call that obtuse. Now, we've got to decide. Clearly, 30 degrees is an example of an acute angle. But as I've just said, 150 also fits this data, but this is obtuse. All right? So we have what is called an ambiguous situation. And that's why some of the lecturers in some of the courses would prefer you not to use the sine rule. All right? I'm saying use it, but be careful. And where in doubt, use the cosine rule, because the cosine rule is never ambiguous. Okay? It's never ambiguous. Now, to show you another example of cosine rule here, this is a good use of a cosine rule. I tend to make up some practical problems, or at least problems with a practical implication, and we have what's called, it's not in your book, but I've actually included this on the video here, a mobile crane application. Just shorten that for you. Now, the mobile crane uses very basic material here. It's got a caterpillar track, it's got a support which is at right angles to the main body. There's S. It has a variable jib, this is J for the jib, and theta is an angle which can be varied by the operator, and joining the two together we have T, which is basically a tie wire. So let's just knock this out. Theta is called a working angle. That can be varied by the operator. T is the tie cable or the tie wire. J is the jib. Okay, that's a fixed length. And S is the support beam, which is at right angles to the body of the crane, and that is also a fixed length. These lengths don't tend to vary at all. The only things that vary are these two. Okay, so let me give you some data. It's very good application and showing you how to use a cosine rule. So the examiner can give you this. Data given. S, supposing it's 15 meters. Very reasonable. J, will that be 12 meters? And angle theta, in this case, we're using a working angle of 70 degrees. And the examiner says, from that, can you find T? Okay, well, let's have a look. So we know this term, we know this, we know this, we don't know that. Now, in this case, one little feature that helps you to use the cosine rule is this. You have two sides and an included angle. So I'll put this in, because whenever you have two sides plus the included angle, then you can use the cosine rule. The other set of circumstances that you can use the cosine rule is if you have three sides that are known and you want to find an angle, you can also use the cosine rule. Okay, so these little bits of information are very helpful to know when to apply the cosine rule. Okay, here we go. We're trying to impress the examiner. We want full marks now for this lot, and this is what we're after. So here's a solution. Okay, the cosine rule, which is in your book there, it's actually written on this page here. I'll just go back to it. Do you notice this? See, here's your sine rule, which I wrote out before. Here's the cosine rule. A squared equals b squared plus c squared minus 2bc cos a. And we can change this around. I'll show you how to do this before we finish this topic, to find the angle, okay, in terms of the three sides. So that's there, and we'll apply that to the mobile crane. Okay, so what we're saying is this, using these two sides. Okay, so we want t. So t squared is what we want. That will equal s squared plus j squared minus 2 times s times j times cosine of the angle, which is theta. Now that's the cosine rule applied to my practical situation. Let me now put the numbers in. S was 15, so this is 15 squared. This will be 12 squared minus 2 times 15 times 12, and this is cos 70 degrees. Okay, now you don't have to do this in parts. This is really good. You can do this in one fell swoop. So let me show you this. To get t equals the square root of all that to there. And your calculator is clever enough to be able to do that if you put it in the right order. So square root, notice it brings the bracket in. Here we go, 15 squared plus 12 squared minus, okay, 2 times 15 times 12 times cos 70. And here you have to be careful. The calculator is very smart. It's actually asked for a bracket there, but notice it's put a bracket here. So you have to bring this off there, and you have to finish it there. So double brackets, okay, bracket, bracket. If you don't, you won't get an answer. It'll come up as an error, syntax error. So watch that. With the Casio, it's very good at prompting for the bracket. You have to be super smart and finish off the actual situation. So in one procedure, knowing these brackets, I now have the answer. So therefore the tie wire for a working angle of 70 degrees, this tie wire has to be 15.68 meters in length. Okay. Now you can measure to the nearest millimeter, so 3 decimal places is not uncommon. That's to the nearest millimeter, 15.680, if the examiner wanted 3 dPs, and you've got the full answer there. In this case, the third figure is 0, but if you wanted 3 decimal places, you'd have to put the 0 in. Okay? So that's a good example of that situation. Now, just to show you the other one that can happen, they may give you 3 sides. So the examiner comes up, it's the same situation here. The data given is now as follows. Support 12 meters, the jib 10 meters. That was close, yes. Nearly had that. And now we're going to set the tie wire at 13 meters. So the question the examiner is interested in your finding is, can we find the working angle theta? And you say, yes, of course we can. Now, if you want to sketch the diagram just to refresh your memory, this is what we've got. Theta, S is 12, jib is 10, this is 13. So now you think, ah, that's right. We have 3 sides. We need to find what the angle is. But 3 sides means invoke the cosine rule. You can use this very nicely. Here we go. Now, you might remember from the book, the cosine rule was in fact written down here, cos A. But there's a question. Some people say, hang on, Mike, how do I get from here to there? If I've got this one, how do I get that one? So I'll show you how to do that. Right, we'll swap it round. Let's write this down. A squared equals b squared plus c squared minus 2bc cos A. Okay, now I'm interested in getting cos A because I want to find the angle here. So again, look, I'll show you this technique. I'm going to temporarily bracket this little lot off, and I notice that all these 2 and b and c multiply cos A. So this is the unit I'm interested in because it's negative. If I swip it to the other side, watch what happens. I pull it to the other side, it changes sign. Okay, so I've got a squared, now I've got b squared plus c squared. Terrific. All I've done is I've grabbed that, brought it across, changed the sign. This is now positive. And then I notice, oh, I don't want this little fellow, so how about I get rid of this? And I can do that. B squared plus c squared don't change. Now this is minus. That comes across and is minus. I'm nearly there now. This is a positive, but I don't want the 2bc. So finally I take the 2bc across and very carefully do the opposite, and I get 2bc. And hey presto, there we are. Now that's good transposing, all right? It means you don't have to fill your head full of lots and lots of formulae unless you're using them every day, in which case you'd remember them anyway. If you can transpose, then all well and good. That's what we're using. So now we've got to be careful. We've got to apply this to this situation here. Let's have a look. Okay, instead of A, clearly it's cos theta. Now A has its partner side over here, so this must be minus 13 squared, because 13 is opposite theta. You must get that right. These two can be in either order. That can be BC or this can be BC. It doesn't matter. All right, so this is 12 squared plus 10 squared, but this is important because the 13 is opposite its partner theta. Okay, notice that? Very important. Over 2 times b times c. Okay, that's the critical. If you get this wrong, it's normally because you get these numbers mixed up. You must make sure that the partner is opposite. Now, again, invoke the calculator and we'll see what we can do. We've got to be a bit careful here. I'll show you a little trick. Nice little technique here that comes in. Again, it can be done in one particular process, but you've got to watch it when you come to the end of the top line. 12 squared, there we go, plus 10 squared, minus 13 squared. Okay, that's the top line. Now, if I keep going and I put divide by, which is what looks to be coming next, if I divide by 2, the calculator thinks that it wants me to do the 13 squared divided by 2. It'll do that bit first, okay, because it's operating in BIMDAS. So what you must do, you've got a choice here, okay. You can now hit equals, and there's the answer to the top line. And for a mental check, you can just stick it down on your paper. All right. Now you can divide by, and this is the bit that you must remember, use brackets. Bring brackets round. 2 times 12 times 10, and close the brackets off. Okay, so the answer, once you hit equals up here, the answer to the top line is done. The computer is completely finished with that. Now you're telling the computer, please divide my answer of 75 by this, by this, by this all together. If you just divide it by 2 and then multiply by 12 by 10, again you get the wrong answer because it's doing a different process. Let's see what we get. Excellent. Okay, so this will give us the denominator 24. This is actually 240. When this works out, you get 0.3125. So now we finally say, good, theta, remember this from before, shift cos, here's my decimal, 3.3125. Okay, now I don't have to change this because I can just hit shift cos answer equals, and there we go. Okay, So theta equals 71.79004314, and these are redundant. Remember what we can do? You've got it. Go back to the DMS button, hit that, and we have a nice little neat package, 71 degrees, 47 minutes, 24.16 seconds, depending on what your lecturer or your examiner says. Rounded off, this would be approximately 72 degrees, which would be fine. So this is the angle. So you say here, theta, the working angle when the situation is 12, 10, 13, the sides are given. Work it through very clearly, showing the steps, and that's quite a good, that's a typical examination problem worth probably 6 to 8 marks, so it's worth knowing really